we go, just into our Oxford College Physics. We've got ourselves some little laser lights up there. There's a green one, there's a red one. What we're going to be looking at in this segment is what is known as dispersion, which ultimately goes with refraction and has a correlation with different wavelengths of light having actually different indices of refraction for a different material, for a given material, excuse me. So what do we have? Well, I've got these two laser pointers that are aligned pretty nicely there, producing a red dot and a green dot right next to each other. And I can go ahead and take some piece of glass here that has some index of refraction, and I can pass them both through it. And they still end up right there. That's good. And they shift their position a little bit. And that's really dependent on where I place this or what angle of incidence they have here. So we get a little bit of lateral shift in their position depending on the entrance angle. But something you should notice is that relative to one another, they stay pretty much in the same position because they both come out parallel to each other because these two surfaces are parallel to one another. So doesn't produce much change. It doesn't really show us that they may be undergoing different angles of refraction while they're inside the material. However, I can accentuate this effect by having surfaces that are not parallel to one another, like in a prism, and ultimately easily show that there are different indices of refraction because there's different paths that the light must be taking inside and outside. So you're looking up there they are right now, and all of a sudden they're going to appear down there. So I'm going to go ahead and take this prism here, and I'm going to let the light go through the prism, and you have a nice angle here so you can actually see it down there. And if you look down towards the bottom, it's really close down there, you get those two dots. But look at how they're separated now. They are not right next to each other because they've taken different paths. Different paths, even though they enter at the same angle, they don't exit at the same angle. And that is because of different indices of refraction for different wavelengths of light in this given material here. So that's what we're going to be looking at. The reason I wanted to demo this first was because I don't want to have to try to align these lasers again because it took me a little bit of time to do, and I don't want to burn them out either by having them sit there for a long time. That's that. So let's just begin. Dispersion of light. Dispersion is ultimately the spreading out of light into its corresponding wavelengths. We'll say the spreading out of polychromatic. Light into its polychromatic, meaning light of different colors or having different colors in it itself, as opposed to monochromatic, light of one wavelength. So multi-wavelength. So dispersion is that ultimately effect of the spreading out. And it is due to the fact that different wavelengths of light will travel through a material at different rates. What does that mean? Well, it ultimately corresponds with a wavelength dependence of indices of refraction. indices of refraction are wavelength dependent for a given material. So the best example of dispersion and really this different wavelengths of indices of refraction is what you view when it's kind of raining, the sun's kind of out, particular angles have to take place, but you see a nice rainbow. What is a rainbow? It's white light, which is a light that is composed of all the visible wavelengths of light, from red, orange, yellow, green, blue, violet, that is broken up into its spectrum, spread out into its spectrum because of dispersion. Dispersion that's occurring due to water having different indices of refraction for the different wavelengths of light. And this produces this spreading out of the different wavelengths and ultimately produces these rainbows. Prisms are another place where we definitely can see dispersion taking place. There's what, like the Pink Floyd shirt or Pink Floyd album, the little prism and some white light going in and the rainbow coming out. And if you've ever seen prisms, you get these rainbows floating all over the place because of dispersion and different indices of refraction. In general, for visible light, index of refraction gets larger for smaller wavelengths. The index of refraction increases as wavelengths What does that ultimately mean? Well, in terms of angles of refraction or changes in direction, it means that shorter wavelengths are going to undergo greater amounts of changes in their paths because they have higher indices of refraction. So we have n sub red is less than n sub violet for given materials. There's generally a spread. It's usually not linear, it really depends on the material, but there's some sort of spread where you have red is say 1.49 and violet is 1.51 for instance, and everything else falls in between those two values. And all the different wavelengths having different indices of refraction produce different paths that they take within the material. So that's what we want to look at now is this dispersion and go ahead and do some problems with it. First off, white light. So light that contains all wavelengths in the visible spectrum, visible region of the spectrum. White light comes from different types of sources, incandescent sources, namely sources of white light. The sun is a nice source of white light. It looks yellow. When we look at it, it's producing white light. Light that has all the wavelengths. Now, it doesn't need to necessarily be an even distribution of all the wavelengths, but it just has to contain them all. So this is why you take some sunlight and pass it through a prism, and you get the actual rainbow, all of the colors, because they're all inside of that light. That's what that light is. It has all those different wavelengths. Some sources only have a few different wavelengths of light within it. And you can see the effects of dispersion by looking at the light from that source as it's passed through a prism or such. which we'll get to later, but most off, I'm going to deal with white light entering some sort of material and looking at the different paths of refraction. And that's basically that. Dispersion's really cool. Not really much to it. It's still just refraction, just different angles of refraction, different indices of refraction for the different wavelengths of light. All right, so let's do some problems. All right, so here's the problem. We're going to take ourselves a block of some material that's transparent, and we are going to shine some white light, or a ray of white light, upon it at an angle of 50 degrees with respect to the normal interface boundary of that block. We're going to say that the index of refraction for the red end of the spectrum is 1.48, and the index of refraction for the violet end of the spectrum is 1.51. All the other colors are in between there. That's kind of the envelope of the visible spectrum there. So I'm going to draw something out really quick just to see what we've got going on. Take this block, something like this, and we got some white light that comes on in 50 degrees with respect to the normal, 45, let's say 50, something like that. Here's our white light. Here's our theta 1, 50 degrees there. And then what do we have? Well, we have some sort of refraction is going to take place, and that's what we're going to get. So I'm just going to draw this out, even though it may not be completely correct. We need some interpretation of what we expect to happen. So we've got red 1.48, violet 1.51. The index of refraction for the violet end is greater. Thus, it will bend more towards the normal than the red end. So let us draw in this violet path. So the violet comes and does something like this. This angle may not be completely correct. We've got something going on at least. And then we've got the red end. The red end's not going to refract as much, but it still undergoes some refraction. It's fairly substantial. Exaggerated a little bit. It's fine. The red end comes out like this. There we go. So what do we have with this? We've got some theta 2 violet and some theta 2 red. So these again are measured with respect to this normal. And we've got this angle here. Let's say theta 2 violet. And we've also got this angle there called theta 2 red. So we go to part A, which asks, what is the angular separation? What is the dispersion angle, it says, between the red and the violet end? The dispersion angle is the angular separation between the wavelengths under consideration, this being the ends of the visible spectrum. So we got this right here. This, generally called delta, equals dispersion angle. Again, the angular separation between the red end and the violet end. So that's what we want to figure out. Part A, delta is equal to what? So how are we going to find that? Well, we just use some refraction, right? We've got, if we look at this total red angle and this total violet angle. If we take the difference between the red and the violet, we're left with this little bit, delta. So theta red, 2 red minus theta 2 violet is going to be that delta. So we can make that delta is equal to theta 2 red minus theta 2 violet. The larger minus the smaller gives us what's left over in between. All right, so it's just a matter of finding what is theta 2 red and what is theta 2 violet. What does that come down to? Snell's law, that's right. We've got Snell's law, which is ultimately the law of refraction that says that n1 times the sine of theta 1 is equal to n2 times the sine of a theta 2 in general. Well, we've got the entrance angle for both the red and the violet is theta 1, 50 degrees. What's different is the angles of refraction theta 2 for the violet and the red because of different indices of refraction. So we're going to assume out here we're in air. Here's our block. Air, n equals 1 for all wavelengths. So we're just going to take that. For vacuum, it's unity for all wavelengths. For air, it's really, really, really close to unity for all wavelengths. So if we just take that there's no real dispersion through air, not measurable anyway, and it's happening within this block. So with this, we just got to do Snell's law 2 times, do some refractions, figure out theta 2 red, theta 2 violet. Let's just do that. We've got ourselves, from Snell's law, solving out for theta 2's, we can move some stuff around and get that theta 2 is the arc sine of n1 over n2 times the sine of theta 1. So let me just generalize that really quick and write that out. We've got theta 2 is equal to the arc sine of n1 over n2 times the sine of theta 1. And then what do we have? Well, we have an n2, n2, which is really n red and n violet, respectively, and a theta 2, which is theta 2 red and theta 2 violet, respectively. So we do this for the 2 different colors. Red. We can go ahead and say that theta 2 red is equal to the arc sine of n1 over n sub red times the sine of theta 1. We can solve that out because we know what n1 is, we know what n red is, and we know what theta 1 is. Theta 2 red is then equal to the arc sine of 1 over 1.48 times the sine of 50 degrees. The arc sine of all of that, calculator in degrees here. We've got the arc sine 1.48 times the sine of 50. We get 31.1712. 31.1712 degrees. There's the angle of refraction for the red end. We'll do the same thing for the violet now. For the violet, we've got theta 2 violet is equal to the arc sine of n1 over n violet times the sine of theta 1, which gives us theta 2 violet is equal to the arc sine of 1 over 1.51 for n sub violet, n times the sine of 50 degrees for theta 1. And we get that. I'll just make a quick little change there. 0.48 to 1.51. And we get 30.4851. 30.4851. 30.4851 degrees. Different angles, right? Because of the differing indices of refraction. So if we want to know what delta is the difference between those 2 angles. Again, delta is theta 2 red minus theta 2 violet, which is 31.1712. Minus what we just got. Gives us 0.6861. 0.6861 degrees. That's a pretty small angular separation, not even a degree, a little bit over half a degree. But there's still an angular separation between the red and the violet end. Within this little angular separation, all of the colors of the rainbow are. They're in there, spreading out. So, let us move on to a part B, which asks specifically, what is the linear separation between the red end and the violet end on the exit boundary of the block? The block's thickness is 5 centimeters. We'll assume that this top surface is parallel to this bottom surface here. So we're going to go ahead and take this block and say that its thickness is 5 centimeters thick, and we want to know specifically what is this distance right here? The distance from there to there. I'm going to call that D. That's going to be the linear separation on the exit boundary of the block. So how are we going to find that? It's a good question. Let's draw this out a little bit bigger so we can see some things. Some of these values will probably be useful still, so we want to erase that. I'm going to draw out this top surface, this bottom surface. I can draw out this normal here that goes all the way down. That's a fantastic. And then I'm going to draw in these wavelengths of light, exaggerate it a little bit so that we can have some bigger picture here. So we've got something like this, right? And we explicitly are asked to determine this distance right here. There's our D. How are we going to get those, right? Let's look at just the violet for a second. It's the closest here to the principal axis, or to the normal. We've got that angle there. That is theta 2 violet. Well, we have that violet from where it comes in, translated down to where it comes out. It's undergone some shift, some lateral shift here. What happens if we call this this distance right here d sub violet? And we figure out what that is. The shift over from the normal that the violet strikes the exit boundary at. Well, if we've got an angle here, we've got this distance between this, it's 5 centimeters. Yeah, we've got a base, got a leg. Yeah, we can figure that out. We've got ourselves the tangent of theta here is opposite over adjacent. That is that this really forms out a nice triangle. It's a little messy as usual. It's okay. We've got 5 centimeters there. We got this distance d sub v there. We got this theta here. So we can write this out that the tangent of theta 2v is dv over 5. Or d sub v is equal to 5 centimeters times the tangent of theta 2v. So that's good. Why is that good? Because we can do the same thing for the red, right? So we've got this angle here for the red, theta 2 red, and we can define this to be d sub red. And what can we notice about this d here? Well, if we take d sub red and we subtract off d sub violet, we're left with d. So, we can note that d is going to be equal to d sub red minus d sub violet. We get the d sub red the same exact way. We've got the tangent of theta 2 red is going to be equal to d sub red divided by 5 centimeters. Or that d sub red is equal to 5 centimeters times the tangent of theta 2 red. And we know what theta 2 red and theta 2 violet are. So we're in a good shape here. So overall, we get ourselves this part B saying that d is going to be equal to d sub red, which is 5 times the tangent of theta 2 red. Theta 2 red is 31.1712. So we've got 5 centimeters times the tangent of 31.1712 degrees minus d sub violet, which is 5 centimeters times the tangent of 2 times theta 2 violet. Excuse me, theta 2 violet, not 2 times theta 2 violet. So we got 5 centimeters times the tangent of 30.4851. And there we go. Compute this out, 5 times the difference of the tangents of those, and we've got 5 times tangent 31.1712 minus tangent of 30.451 gives us 0.0812. 0.0812 what? This is centimeters here. So this is centimeters here. So gotta be a little careful with that. That is centimeters. Well, if we wanted to change this to say millimeters, we could write this in millimeters. That is 0.812 millimeters. Not even 1 millimeter spatial separation. This distance is really, really fraction of a millimeter. So the question becomes, can we see that? Can we see the red versus the violet? Can we see the rainbow? The rainbow is packed in this 0.8 millimeter space. You're not going to see a rainbow. That's sad, huh? That makes me sad too, but we'll fix that later on. But for now, just go get a really small spatial separation. Now it turns out that the thicker this block is, the larger that spatial separation. This angular separation will always be the same, which we calculated to be 0.6861 degrees. This angle here. That stays to be that angle of 0.6861 degrees. The longer this has to travel through the material, the greater the spatial separation. Up here, the separation is much smaller than down here. If this block was twice as thick, well, we'd have a lot more linear separation. But 5 centimeters for like a block of, say, glass or something, that's pretty thick. That's from here to here. It's some like bent glass. Nonetheless, we don't see any rainbows. And that's typically the case for like passing through glass. We see rainbows everywhere because there's not enough separation, linear separation. And, well, we've also got, that's at the exit boundary. What about after they exit back out into air? So what happens when we say, well, it's going to come back out into air? For us to see it, it has to reach our eyes. We'll assume that we're not inside the glass, that we're outside of it. So I'm going to look and say, do I see this rainbow or these different edge colors? So the question for part C is, what is the angular separation between the red and the violet end upon exiting the block, coming back out into air? Well, we've just got some refraction that takes place again, right? Now we're going from the block out into air. So let's erase that really quick. That's okay with you. And what are we going to have? I'll just draw one of them in. We've got ourselves a normal here. Let's do this one. Let's do this one. Put ourselves normal to that interface boundary. And we'll have some sort of refraction takes place. Now we're going from a higher index to a lower index, and we will get that comes back out. Oops, let's just do like this. Comes back out, maybe something like that. We want to know what is this, we'll call this angle to deal with. We'll call that theta 3 violet. We'll call that theta 4 violet. And red's going to do the same sort of thing here. It's going to come out, and we'll have some theta 4 red. These get a little bit messy, draw a whole bunch of references, but like that. For the normal, red exits some angle to be determined. We want to know what's the angular separation between the red end and the violet end. Well, here is theta for violet measured from its normal. All right, so the dispersion angle now, we call it delta 2, is going to be equal to theta for violet minus theta for red, or vice versa. Let's do red minus red. Let's stick with what we did before. Red minus violet. All right, so how are we going to get those theta 4s? Again, we're going from a theta 3 here to a theta 4, so we can write something out in general. We've got ourselves, we'll say for the violet, let's do the violet first. T. for the violet. We've got, now we're going from violet at some angle theta 3 back out into air at some angle theta 4. So I'm going to rewrite Snell's law according to what we've got going on here. N sub violet times the sine of theta 3 violet is equal to N sub air times the sine of theta 4 violet. Going from to. We wanted to figure out what theta 4 is. We better be able to figure out what theta 3 is. So how are we going to get theta 3? Well, we've got parallel surfaces here. So look at a little geometry, figure it out pretty quick here. If I take two parallel lines, and I take something like this, got this angle and this angle, theta, theta, same angles. So if I measure them relative to a normal that's aligned the same, 90 degrees, well, this angle phi has to be equal to that angle phi as well. And those are the angles theta 2 and theta 3. So ultimately, this is just to show theta 2 is equal to theta 3 for our picture. Use some different angles there, but ultimately, that's it. This. Theta 2. Probably should have named them different, but we get the picture there. Anyways, we already know the theta 2s, so we already know the theta 3s then. So we are in a business because theta 2 and theta 3, violet, theta 2 violet, theta 2 red, thus theta 3 violet, theta 3 red. So I'm going to erase this. Just note, theta 3 violet is equal to 30.4851. And theta 3 red is 31.1712 degrees. There we go. We can go ahead and use this. Violet. We've got that theta 4 violet is what we want to solve for. So move the n arrow over to this side, take the arc sine of both sides, and we've got theta 4 violet is equal to the arc sine of n sub violet divided by n sub air times the sine of theta 3 violet. Seems welcome enough. All right, so let's just quantify this out. Theta 4 violet is then equal to arc sine of n sub violet, which was 1.51 divided by the incident fraction of air, which is 1, times the sine of theta 3 violet, which was our 30.4851 degrees. And we get ourselves, watch this, amazing. All right, I'll just put it in my calculator, just to be like I'm doing something. 1.51 times the sine of 30.451. Oh, that's weird. It comes out to be 50.0000. Wow. 50.0 degrees. What angle did it first enter at? Oh yeah, N1, that was 50 degrees too. What do we have? An exit at 50 degrees. Well, yeah, because it's just going back out into the same substance that it was originally in, and these surfaces themselves are parallel to one another. That's always going to be what we're going to get. Let's look at theta 4 red. Theta 4 red is going to be equal to the arc sine of n sub red, which was 1.48 divided by 1, times the sine of theta 3 red, which was the 31.1712 degrees. And guess what that comes out to be? That's right, 50 degrees. Okay, what's the angular separation between these? 0. They exit parallel to one another. So, what do we end up getting? There's no angular separation. Whatever the linear separation is here, well, that's preserved within this. This is a little bit of a different distance here than that, but they're related to each other geometrically. The point with this is that the whole rainbow is wedged within this little tiny distance here, which is a fraction of a millimeter. You ever gonna see that? You put your eye here, whoosh, you see the rainbow? You do not. Maybe you see that the glass has a little tinge of reddish, violetish to it, because you've got this separation of those ends there, but you don't see the whole rainbow. Some other things just of general interest is we can separate things out more by having the block larger and larger, but realistically, we're not going to see a rainbow with this. There's other ways that we can produce some ongoing divergence from the red and violet ends and get this nice angular separation that produces a big linear separation with respect to the ends of the spectrum. But that's really it. That's what we got. That's it. All right. Thank you.